This is a really interesting experiment I did. People talk about, there's really three things we can do to protect ourselves from radiation. And the cardinal rules are time, distance, and shielding. In other words, what's time mean? Minimize the amount of time you spend near the beam, near the x-rays, right? Distance, increase your distance away from the beam. I'm not sure we'll have time today, but there's actually what's called an inverse square law. Every time you double the distance, the intensity quarters. It's the inverse square. So if you take your distance and go twice as far away, you have 1/4 of the radiation hitting you. Another, twice away, 1/16. So it really decreases exponentially with distance. And the third is shielding, putting lead, walls, metal between you and the beam. So time, distance, and shielding are the three things that you'll learn for radiation safety. What I did here, look at this picture. This is an over table x-ray room. And you can't see it from where you're sitting, but here's the collimator. See the light right there? I'm collimated down to this detector on this little sensor. I put a detector next to the detector. It's not in the beam at all. In this detector is what's called an AED, automatic exposure. I forget what the acronym stands for, but it's an aftermarket detector that basically will trigger when it sees radiation. So it doesn't require any interface with the generator. You can just plug it in. When it sees radiation, it starts to trigger, and it stops recording once it sees the radiation stopped. And look at the image on the workstation here. What do you see? Keep in mind, this is the actual image being taken. So the AED, not only, there's enough scatter radiation to not only trigger the AED from reading, but also show you an image. So it just goes to show scatter is a real thing, right? That was the whole point of this kind of experiment. I expected nothing. I thought it was gonna be like minimal. There's quite a bit of scatter. The point is time, distance, and shielding. Keep yourself away from the beam, and that demonstrates why, right? See that meter? That meter is in the image of this detector, but it's not part of the actual collimated field of view in that case. Just kind of crazy. Sure, let's hear it.
Like STD is your enemy on X-ray.
What is your enemy?
STD.
Oh, that's true. Shielding time and distance, your STDs, that's right. Good in imaging. Bad elsewhere. We just talked about this. This is just describing that previous slide. And we've already talked about how grids work, right? You have these lead veins that allow primary photons through, and they block the scatter radiation. Again, what's the problem with scatter radiation? Increases dose and doesn't contribute anything usable to the image. In fact, just the opposite. This is just going to a historical perspective, how images were first recorded. So this is back in the day of film and wet processors. X-rays would hit an intensifying screen, which would glow. The light would expose a film. You take that film to a dark room, run through a processor, you're left with an image. That's like when you see the movies, a doctor holding a piece of film in their hands, right, up to a light box. Now it's all digital, which we'll see here in a second. CR cassettes you may have heard of, or these are like a flat panel that's portable. The advantage with these is they can retrofit and go into a Bucky. So if you want to take a system that was analog only and convert to digital, you could use a CR cassette or a wireless detector that will fit into a standard Bucky. So a lot of systems now use wireless detectors like this. Remember, the Buckies could be a table or in the wall stand. So what are this one detector then could be used in a table for one exposure, move to the wall stand, do a chest shot, the same detector. They could even take that detector to the next room over and use it in multiple rooms. So what are some pros and cons of these portable detectors like this? What's some pros? Cost. Yeah, well, first of all, they're cheaper than fixed detectors. And now we just talked about using one detector for 2 receptors or multiple rooms. Yeah, so definitely less expensive, more economical. Oops, skipped ahead. Cons. No, that never happens, right? So yeah, these things get abused because humans are handling them. Even between exposures, they're going to get dropped. They're going to get damaged. Manufacturers will put drop sensors in these and void warranties once they get above a certain amount of drop levels. There's actually like an accelerometer built in there, and it hits certain G's, a certain number of times, you can void warranties with that. So yeah, less expensive. Yeah, it's portable, but the problem is it's portable, and humans are interacting with it, and that can cause a problem. But if you had a rad room with a chest stand and a wall, or a chest stand and a table detector, and that increases your cost by easily a couple $100,000. So it can be a very economical method, these portable detectors. Fixed detector means that the actual detector is permanently mounted either in the table or in the wall stand. Those of you guys that work on imaging already, do you see predominantly portable, fixed, mixed bag? What do you kind of see in your mostly portable? Do you? I know TKA, you guys do a lot of digital diagnostics. Those are probably mostly fixed, although they might have the WPD option. You guys use the portable detector with that as well? Because they have the portable and fixed within the same room often. Yeah. Okay. Computer radiography, I'm not even gonna get into this. It's not even used anymore. Reimbursement rates made CR, this is computer radiography, where it would basically take the place of a film cassette and now digitize it. But because of reimbursement rates with Medicare, Medicaid, this is kind of antiquated technology. Anybody here still using CR? I'm sure not, right? All digital? Okay. Let's talk for a second about digital detectors. Slide 26. So a detector has a digital matrix just like a camera would. When someone says that their camera is 1 megapixel, what does that mean? What's mega? Million. And it basically has an XY axis, right? With rows and columns. So a 1 megapixel camera means you have 1,000 rows and 1,000 columns. Agreed? 1,000 times 1,000 gives you a million. So megapixel is just telling you how many millions of pixels that particular camera has. Ultrasound, anybody, I'm sure somebody here do ultrasound. A typical ultrasound matrix is 512 by 512. CT is typically 1024 by 1024, which is about a megapixel. DR and CR is going to be about 2K by 3K, so 6 megapixel. Mammo is the highest resolution out there, like Hologic Selenia, for example. Theirs is 4K by 3K, so 12 million pixels. So it's referring to the number of pixels that are, in the image, which is strictly, just keep jumping, dealing with resolution. What gives you better resolution, small pixels or bigger pixels? The smaller pixels, better the resolution. Yep. What's the trade-off though? But why not just make these pixels? I mean, we have technology to make pixels way smaller than 512 for ultrasound and 1024 for CT. We can go way smaller than that. Cost, and how about when you start increasing pixel matrix? What's happening now? Processing speed, processing time, amount of data I have to transfer and store, all those things become exponential. I mean, think about 1 square and you double your resolution, you've quadrupled your storage requirements now, right? If you take this pixel that was this and now you double your resolution, you have 4 times the data you have to deal with and process and store and transmit, all that stuff. In fact, nowadays, the limiting factor for imaging is not the detector technology at all. It's the processing and the computer power to be able to keep up with the images at that resolution. So this is kind of a detector, what it would look like from the top view. This is what a digital detector would look like from a cross section. And the whole objective here is to convert analog into digital. Photons are analog, and the digital is the image on the screen we want to see. That's the whole objective. But there's 2 technologies that can do this. Every digital detector out there today is either indirect or direct. What indirect means is the X-rays first get converted to light, and then that light gets read by what's called a TFT, a thin film transistor. Guess what this does? Converts light to electrons. Okay, so why is this called indirect? Because this layer here is converting radiation to light, and this layer here is converting light to electron. Okay, so now down here I have charge, and there's going to be a capacitor below here that is going to draw in the charge from each pixel. So there's literally going to be a capacitor down here storing a voltage, which is going to be representative of the radiation that struck that area. The voltage in that capacitor, is that analog or digital? It's a voltage, it's analog. It's a capacitor storing voltage. So how do we get to digital? Run that cap through an A to D, and it converts that number now to a digital number, which can be at 8 bits or 10 bit or 12 bit or 16 bit, which we'll get to kind of in a second. So this is indirect. Most detectors on the market use this. All Philips detectors, all Siemens detectors, all GE detectors. Pretty much everybody out there now has indirect technology. The only manufacturer really using this widely is Hologic with their MAMO, with the direct detectors. And what the direct detector does is it converts X-rays directly to what? Electrons. So the Hologic's MAMO product is called the selenia dimensions. Selenium is an element that occurs in nature. And if you look up selenium, it's a photoconductor. It conducts with photons. In other words, when photons strike selenium, it gives up a charge. So now I have electrons floating around in this layer of selenium proportional to the photons that struck it up here. But here's a good example. Now I have this transistor, and there's a thin film transistor and a capacitor. So when this transistor turns on, it acts like a switch, and it draws the charge from here down to ground, which charges that capacitor. So now I have a capacitor, a voltage representative of one of these. Are you with me? So that one, every pixel has a capacitor and a transistor tied to it. So these things, when you're talking about a MAMO detector that's a 12 megapixel matrix, 4,000 by 3,000, there's 12 million pixels in an area the size of a sheet of paper. There's 12 million capacitors, 12 million transistors. So what I'm getting at is there's no repairing these things, right? These are all clean room, under a microscope, built by robots. These detectors go bad. Anyone out there that says they're repairing detectors is not repairing detectors. You know, we at RSTI test and repair parts. We're not fixing the components are too small, but there's PCBs in the detector that we can take 2 or 3 detectors that are bad, make one good one. You know, that's being done in the industry, but you're not repairing the stuff. It's too small, you can't even see it. It's, you know, it's all done under a microscope. And these detectors can, you know, just like the X-ray tubes, are really, really expensive. Detectors can be 30K on the low end, up to 200K on the high end. So your X-ray tubes and your detectors, those are your 2 big ticket items on any X-ray system, right? Any questions there about the detector? What's the objective of any detector? To convert photon energy into digital, ultimately digital, yeah. Yep, we're gonna create a voltage, read that off, and convert that to a digital number. I'm gonna spend a lot of time on this one here, but we're gonna talk about the analog to digital converter. Now that we have a voltage, we have to convert that to a digital number. So if you had a 8-bit value, remember 8 bits, right? It goes, you know, 2 to 0, 2 to the 1, 2 to 2, 1, 2, 4, 8, 16, 32, 64, 128. And 8 ultrasounds are 8-bit A to Ds. How many possible combinations can you have with 8 bits? 256, 0 through 255. So you would have, with ultrasound, it keeps doing that. If you look at an ultrasound image, there's a lot of black, there's a lot of white, there's not a lot of contrast in the middle, right? They're very high contrast because you have your white up here, your black here, and you've got 256 different shades of gray. Well, if you had a 9-bit A to D, how many shades of gray would that give you? 512. 10-bit, 1024. 11-bit, 2048. 12-bit, 4096. And let's call it 8K and 16K. So 14 or 16-bit is what like a MAMO or a DR rad room would use for A to D converters. You can still only have black or white for the pixels, but by having more bit depth in the A to D converters, what do you have? More shades of gray. So ultrasound has big steps between the different colors, between the contrast values. MAMO or rad shots can still be black or white, but they have thousands more possibilities, which are better used for measuring contrast. Does that kind of make sense? Okay. Especially important in mammo, we talk about where the breast tissue is very similar, adipose, glandular, and fibrous. When you have very similar tissues, it's contrast that allows you to see differences. Resolution allows me to see small things. Contrast allows me to see differences between those different pixels. Okay, so two very different things. So what determines resolution on a detector? What component determines how good the resolution is? Size of the pixels. Agreed? Smaller pixels, better resolution. What determines the contrast capabilities of the detector? The A to D bit depth, 8 bits, 10 bit, 12 bit, 14, 16 bit. Yeah. So it's the conversion from analog to digital that gives you contrast. It's the small pixels that gives you resolution. And different modalities want different things. You know, mammo is more concerned about contrast. They're not as concerned about the resolution. We have the ability to see small things, but I need to be able to see differences in those three tissues in the breast. That's what really differentiates, you know, seeing adipose tissue and cancerous tissue. Very, very important that we can see those contrasts, especially in mammo. So I just gave some examples here of different bit depths, right? This could be like a 4-bit. In the increased bit depth, you can see it's the same image, but when you have a lower bit depth, it's taking all the similar shades of gray and making them into one, right? And you're losing that information. So lower A to D converter, higher A to D converter, more shades of gray. Pixel size we talked about, right? Big pixels, smaller pixels. That's the difference between resolution and contrast. Obviously, more pixels improves resolution. I'm gonna jump ahead here because we're running out of time. Let's go to this slide. I'm not sure what slide number this is. Slide 34, page 17. In the first part of the class, we talked about the factors of the image being kVMA and time. And this slide talks about the factors the customer wants to see, which is the resolution and the contrast. So the terms that the customer is going to use is density. What's density refer to? Yeah, how light or dark that film is. If the image has too much density, there's too much penetration. Too dark of an image, not enough absorption. It's too dark, okay? So density refers to how light or dark the image is. So this would be high penetration, this would be high absorption. It would cause those two things. What is contrast a measure of? The ability to perceive, to distinguish different densities. So why is this high contrast and this one's low contrast? Because there's a big difference between those pixels. There's a small difference between those pixels. Does that make sense? What determines that? The A to D converter. 8-bit A to D converter would give you higher contrast because the differences in the steps is a big jump. A higher bit depth, a 10-bit, a 12-bit, a 14, 16-bit would give you lower contrast, because there's a smaller step. So you can't really say better or worse contrast because it depends on what you're looking at. It's higher contrast versus lower contrast. You know, in mammo, you want low contrast. Otherwise, all the breast tissue is going to be absorbed or penetrated. You're going to miss the cancer. So it depends on what it is they're looking at. So density, how light or dark the image is, and contrast is different shades of gray. Slide 35 talks about distance. Here's a few terms you're going to see: SID, OID, and SOD. Well, up here on the board, I put the names. Source to object. Oh, wait a minute. Typo. Sorry about that. SID, source image distance. So what does SID mean then? What's the source? The X-ray tube, the focal spot, right there. What's the image? The detector. Yep. So SID, source to image distance, is the distance in this picture from A to C. The source to image distance. OID is the object to the image distance. Where's the object in this picture? B. The image is still C. So B to C is the OID. Back to my handy dandy photon creator, right? By moving my hand, I'm not changing the SID. The source, image, distance remain the same. The object image distance is changing. What's happening? Mag factor, right? As you have a increased OID, object image distance, here's the image. As I increase that OID, I have an increased mag factor. And what happens to my resolution? My fingers, they're blurry. When I get down here, they're sharp and crisp. So you want to have a lower OID, be as close to the detector as possible. And what's SID? What would I be changing if I was changing my SID? Yep, the tube or my phone in this case. Why is a change in SID going to give me a better resolution? Look at my hand right here. Now as I get away, yeah, slightly, there's a phenomenon called penumbra, which is the blurriness around the edges that goes away as I increase the SID. And you have, so bottom line is you have better resolution by being further away. It increases your resolution. What resolution or what SIDs are typical? You're gonna see most all the time. Maybe know those used commonly. 40 inches and 72. So 40 is gonna be a table shot, usually like a table detector for an extremity. 72 is usually gonna be a wall stand, AP or PA chest shot. And source to object distance, what would that be? Distance between what? A to B. Where that comes into play is you're doing calibrations. You're reading the Phillips manual, for example, and they tell you to put your dosimeter at a 30 centimeter SOD. What do they want you to do? Put your dosimeter at a 30 centimeter SOD. 30 cm from the focal spot. They're telling you where to put your detector in measuring dose, what they're doing there. So the customer will use SID and OID often. Service engineers will use SOD because there are different requirements for different calibrations. This chart here on page 36, honestly, we could spend a whole day alone on this. When you come into phase 1 or phase 2 at RSTI, the objective, we're going to teach you not to memorize this chart, but you should be able to look at these things along the left and explain to me. You know, so for example, you should be able to tell me now, why does KV affect density? Anybody have any thoughts? Why does changing the KV affect how light or dark the film is?
needs to have more variability in darker
And so that's quality. The quality of the beam is changing, and the quantity is also changing because now I'm pulling more tube current across there. So by changing the kV, it's going to impact how light or dark the image is going to be. Does that make sense? Why does changing the kV affect the contrast of the image? Remember, contrast is a difference in shades of gray. So by changing the kV, it's going to change the penetration and the absorption, which is going to directly affect the contrast. That makes sense? MA affects density only, but not contrast. Think about that for a second. See if you can explain why. So going back to my X-ray tube from earlier. Right, this is MA, going between there, agreed? If I change the MA, I'm gonna change the quantity. I have more or less photons. I didn't change the power of those photons, which means the balance of penetration absorption didn't change, but I have more or less of them. So it didn't change the contrast because the penetrating ability and the absorption balance remained exactly the same, but it got lighter or darker. Does that make sense? Same thing with time. I think if you look on that chart, time also only affects density because, again, the number of photons is going to make it lighter or darker. They're not any stronger. They're not any weaker. They're not penetrating more or absorbing more. It's just a pure number, lighter or darker. So I'm not going to sit here and go through this whole chart. You guys like think good. But that's kind of the idea behind this. You know, what does SID affect? What does OID affect? What do grids do? What do collimators do? Filters, you know, all those things that we should understand, kind of the physics of how these changes impact the systems. Let's skip ahead to page 37. Probably hard to see here, kind of a small diagram. This kind of is the fundamental, the concept for which every X-ray generator works. And I kind of on the left-hand side broke this down into the basic categories. Top left corner up here, what's happening? Incoming AC. So that means if it's three-phase, it'd be 480 volts, right? 483 phase. So 483 phase from the customer's wall box, the power breaker is coming into the room. What am I doing here? I'm filtering that and converting it to DC. Okay, so this is an inverter. I'm taking 480 AC, I'm filtering it and converting it to a fixed DC supply, probably 600 volts to 800 volts DC. Okay, why am I doing this? Because I can control DC better and faster and more efficiently than I can AC. AC, I have to wait for the wave to pass over zero crossover to turn things on and off, right? Which when you're talking about milliseconds or microseconds, that can have an impact. But with DC, I can turn things on and off really, really fast. So we're taking AC, we're converting it to intermediate DC. This guy right here is called the high voltage inverter. I'm gonna pass this DC through this guy. This is the high voltage transformer. You can't pass DC through a transformer. Everybody agree? So what do you think this inverter now is doing with this DC? It's a high frequency inverter. It's taking IGBTs and chopping them up. So there's a signal coming from the computer saying, I want you to fire these two, then these two, then these two, then these two. And what's happening is I'm passing DC through the transformer to make it look like AC. And again, the whole purpose of this is that I can more quickly and accurately control the DC than I can the AC. So this is really what's producing my kV, my kilovolts. I'm firing this inverter to give me a certain voltage, but only a fraction of it. What's the transformer's job? What's any transformer's job? Step up or step down? In this case, it's stepping up. So let's use some easy math and say that this high voltage transformer had 1,000 to 1 turns ratio. If you were to cut open a transformer, what is it? A bunch of wires, right? It's coils. You got a primary and a secondary, you got input voltage, you're gonna step up or step down the voltage on the output side. So the job of the high voltage transformer is to just step up the voltage that was made by the inverter, okay? So let's use 80 kV as an example because that makes for our easy math. And this was 1,000 to 1 turns ratio. How many volts is the inverter going to make? 80 volts, right? Plus and minus 40 more specifically. Remember the anode and cathode? So this guy's job here, the inverter, is gonna make negative 40 volts and positive 40 volts. That voltage then goes into a bunch of windings, which are in oil, high voltage transformer, because it's got 100,000 volts in it, so it can't be exposed to the air. So that's what the high voltage transformer is doing, is taking this voltage coming into here and making your 80 kV, 90 kV, 100 kV, whatever it may be. And then from there, where's it getting applied to? The X-ray tube, right? And so this is just showing not the actual formation of the image, but how the high voltage is produced. So we have logic and control, which is controlling the high voltage, which would be the orange in this case. Like pick your time, pick your MA, you know, the control for actually making the high voltage. And then we also have filament control as well. Why do you think the filament current might change, for example? Why would you have to change the filament current? Yep. Let me go back again to my X-ray tube slide here. We all agree that filament current is running through here, right? We all agree that tube current is running through here. We all agree that kV is the difference between those 2 points there. If filament current was, let's make up something, 3 amps, and you change the kV from 80 kV to 100 kV, what's going to happen to your tube current? 3 amps of filament current over here, and you increase the kV. The tube current would go up because now there's more potential sucking those 3 amps across. But when the doctor says, I want 100 MA, they mean, I want 100 MA. I don't care what the kV is. They want independent control. So the system, when we calibrate these, we have to have the ability to change the kV, and there's going to be a different filament current. It might need 3 amps at 80 kV and 2.6 amps at 100 kV and 2.2 amps at 120 kV. So that's all things that we're going to calibrate when we're doing our filament calibrations to ensure accuracy of the MA. We don't care what the filament current is. The customer doesn't care what the filament current is, but they do care about the tube current because that gives you your density that you want on the image. The point is this section down here is controlling the filaments, and this section over here is controlling the high voltage. Okay. But I used the analogy when we first started this morning about the internal combustion engine, air, fuel, and spark. You open up a GE schematic of any X-ray system, you're going to find these components. You're going to find incoming AC that gets rectified to DC, filtered, chopped up, sent through a transformer, applied to an X-ray tube. You open up a Phillips block diagram, guess what you're going to find? The exact same thing. So the idea behind our classes at RSTI is to teach you the fundamentals. So when you open up a book, I can't teach you every X-ray generator, but I can teach you how they work. So I've never worked on the Siemens Axiom Artis, but I can tell you, I can figure it out because I know the fundamentals, and I'm gonna take this right here and apply it to what Siemens is doing. Okay, all those concepts are the same. So in summary, what am I doing here? Bring in, what's the voltage I'm typically bringing in from the hospital? 480 3-phase. Could be 220 single phase on a smaller room, but usually 480 3-phase. What am I doing here? Rectifying. I'm taking that 480 3-phase and making a DC voltage 600, 800, 1000 volts or whatever. Why am I doing that? Faster, more efficient, easier to control. I'm then taking DC, I'm running it into the inverter, whose job is to do what? Chop up that DC and pass it to the high voltage transformer, because you can't pass DC through a transformer. So we got to chop it up, make it look like AC, and then we can pass to a transformer. And what's the job of the high voltage transformer? Step it up. Yep. Step it up to whatever kV the customer asks for. And does it make sense if it's a 100 kV exposure, you'd have plus 50 and minus 50 here, right? Any X-ray system in the world works like this. A dental unit, a GE rad room, Philips CT. If it makes X-rays, it's going to do this exact same thing. I mean, the difference between this, when you add CT into the mix, what's the big thing that has to change with CT? It's spinning. It's rotating around axial slices of the body. So where's the challenge here? How do I get this on a turning gantry? And what vendors usually will do is they'll put a slip ring either here or here. So now I'm going to pass that voltage on brushes onto a rotating ring that literally drags along the rotating side and passes that voltage. And all of this stuff right here, guess where it is? It's all on the rotating side. So all this stuff inside here is spinning at 6 to 8 revolutions per second, which if you do the math ends up being about 19 Gs, 20 Gs. So a 200-pound X-ray tube all of a sudden weighs 2.5 tons, which is why CT torque spectra are really important, because all this stuff that's in here, the tube included, is all spinning. And have you ever seen a CT spin with the covers off? It's pretty intimidating. If patients saw that, they'd never go inside, right? It's kind of scary. The only good thing is if something goes wrong, which way is it going? It's going out, right? Spinning at 19, 20 Gs is going to go out. It's pretty intimidating. Same thing. Exactly. Yep. Yeah, high voltage multiplier, high voltage transformer, HVT, all different names that they'll apply for that. Yep. So that would be then this guy, the multiplier. Where have you heard that before? Was it Hologic? Because that's what they call theirs. So Hologic calls it the inverter and the multiplier. Well, you can see right here, this is what they're doing. What's the inverter doing? Chopping up that DC. What's the multiplier doing? Stepping it up. That's a great example of a manufacturer. They give it a different name. They call it multiplier, but I understand X-ray, so I know what they're doing. They're taking the inverter, chopping it, and multiplying it. Yep, excellent point. This slide, slide 38, now we're getting into RNF, radiographic and fluoroscopic. What's the big difference between fluoroscopy versus everything we talked about so far, which has been rad? What's fluoroscopy? How's it gonna be different? Moving, dynamic, video. Everything to this point has been still shots, 2-dimension, taking a picture, right, with your phone. Now we're talking about taking a video and capturing things in motion. So what you'll see here is there is an over-table X-ray tube. Why do you think they call it an over-table tube? It's over the table. Well, guess what? There's an under-table tube. Guess where it is? Inside the table. So the point is, an RNF room has 2 tubes, 2 X-ray tubes, 1 generator, 2 tubes, so you can only use 1 at a time. The over-table tube is going to be predominantly, well, exclusively used for what type of exams? Still radiographic shots, 2D. The under-table tube is going to be used for fluoroscopy, video, moving, motion, things like that. So the over-table tube, in this picture is here, shoots this way. The under-table tube is in here and shoots this way. So you have 2 different systems that work here, right? You've got over-table tube and a detector, and an under-table tube, in this case, an image receptor or an II or flat panel, depending on the technology being used. I have a little bit more mechanics down here now. This table can tilt, like for barium swallow. They'll have the patient drink the barium, and they'll tilt this at a 45 or 90 and take the shot that way. so they can get the barium aluminum to coat the intestines. So a little bit more going on here with the geometry and motion control stuff. This slide here looks like slide 38, page 40. And this is just kind of showing you again the guts of what's inside there. So just so we're clear, this over table x-ray tube, where would images from that be captured in this picture? Either this table bucky or the wall stand. Agreed? Over table is going to take x-rays here or here, 2D static. Under table, where are those photons going to go? This guy, image intensifier. So the job of the image intensifier, we're going to see in a second, is to convert x-rays to electron. Sound familiar? Just like a detector. But in this case, we're doing it for the video and the moving aspect. This slide here, slide 40, this is what the image intensifier looks like. The next slide is kind of the guts of what's going on inside there. This is slide 41. So entering the input phosphor, what comes in down here? Photons, x-rays come in here. This input phosphor converts photons to electrons. Electrons flow through here. We can steer them actually with these grid voltages. And then the output phosphorus job is to convert electrons to light. That makes sense? Because now with cameras can't see electrons, right? I can't put a camera on here and look at electrons. So the job of the II is to take photons, convert to electrons, electrons to light. There's gonna be a camera right here. It's gonna capture that at a frame rate and show you a video on the monitor. Okay. And this goes until, is it noon? Is that right? We got 12 more minutes. Just trying to pick and choose what is important here. Yeah, I mean, the next slide on page 21, this is just kind of showing you fluoroscopy, x-ray tube, image intensifier. Here's some kind of optics. And then I'm shining the light into a camera that processes that, goes to the generator, and kind of is this closed loop circuit and displays the image up on here. Okay. Well, yes and no. I mean, anybody here have OEC arms in your facility? You know, they're still IIs. The CFD is the CMOS slide detector. That's a flat panel version. So yes, manufacturers have flat panel replacements for these, but there's still tens of thousands of systems that are gonna be around for a long time with this exact same technology. I mean, who in here has an OEC 9900? Raise your hand. Everybody. I mean, they are. 99s are old. But the CFD is the CMOS slide detector that replaced the II with a detector, but still an OEC. But my point is, they've 9900s, they were selling those until 2 or 3 years ago. It's the most popular CM in the world. They're going to be around for a long time using this exact same technology. Yep. No, good question. And then, you know, to your point, here's a modern system. So we teach the Siemens, what is this, Luminos Agile. So this is an RNF room. What do you notice is missing? There's no II. So right here, you can't see it, but here's the over table tube, right? Here's the under table tube right there, you can see it. And there's no II. How come? It's a flat panel detector. So now manufacturers are getting away from that technology and replacing them with flat panels. The problem has been until recently, the detectors couldn't they couldn't convert to an image fast enough. Because think about it, there's no such thing as live video. What do I mean by that? Everything is still images. Your GoPro has a frame rate of 30, 60, 120 frames per second. Your iPhone, your Android is capturing video at a certain frame rate. Hollywood video, the highest end cameras in the world are capturing at a frame rate. Why is there no such thing as live video? I can't read an image and convert it to digital and transmit it out simultaneously. So it's read, integrate, read, right? It's having to read the image, pause for a second, and transmit that off to be read and analyzed, okay? This slide here, I'm jumping ahead. I'm jumping around here because we're running out of time. So let me go back. This slide here on slide 46, this is a little bit about different detector sizes. If you work around cath or cath labs, angiography is a study of vessels and veins. Cath is a study of the heart, right? So there's different detector sizes manufacturers will have depending on the type of exam that they're doing. If a cardiac room is looking at just the heart, small detector. The human heart is the size of 2 fists put together. If you take both of your fists and put them together, that's the average size of the human heart. I don't need a detector 17 by 17 to see this, okay? I can do the small detector. So a cardiac room is gonna have a small detector. So if you have GE systems, they're gonna be the GE 2100, Innova 2100 or the IGS 520. The 21 is the size of the detector, 21 cm by 21 cm. Their 4100 is an angio. So that's 41 centimeters, or the IGS 540. So angio means vessels. So if I want to look at a clog in a leg artery, it's running down the leg. My detector, if it was only this, I can do angio studies with cardiac, but I have a lot more images. The detector is smaller. If I have a bigger detector, now I can capture that same leg in less shots, which means faster study and less dose to the patient. So that's why they have different sizes of detectors for cath and angio, because angio is all over the body and moving, and cath is in the heart and the torso and doesn't move. Okay, that's kind of what this is describing here. And the irony is in this is these are the GE detectors. Where is GE headquarters? Waukesha, Wisconsin. So they measure their detector sizes in 2100, 31, 4100 millimeters. So the US company uses metric. Where's Philips? Netherlands. And their detector is the FD10 or FD20, which is inches. So the European company uses inches for detector sizes, and the American company uses metric for theirs. I have no idea why. Just interesting. Let's see here. Let's triage what's important. Tell you what, let's go to this slide here. This will just kind of, I'm not going to go over gridded x-ray tubes, but if you go to slide 56, page 28, this should reinforce the difference between KV, filament current, and tube current. So I know the answers are already filled in on your slide number 56, page 28. But this example number 1, if you have no KV and no filament current, you can't have tube current. That makes sense, everybody? I have no KV here. I have no filament current. There's nothing going across here. No radiation being produced. This next example, I have KV is off, filament current is on. How much radiation is being produced? None. There's still no tube current. There's nothing to suck it across there. So I have filament current here. I have no KV, and I therefore have no MA. This example has KV on, but filament current off. Still no radiation. I have a big voltage across there, but there's no current flowing, so no electrons to be sucked across there. No tube current, no radiation. Yes, sir.
So, again, on the screen, what is it again?
Nothing. Zero. The detector is sitting there. There'd be no trigger. It wouldn't be triggered for an exposure. But manufacturers will do this. They will leave the KV on and only control because it's a lot more power to turn the inverter on and off, they'll leave it on, and they can turn the filaments on and off to what's called for pulse fluoro. Yeah, you wouldn't see any, so none of these so far have made any radiation, no x-rays. Now I've applied KV, I've applied filament current, and now I have tube current, which is MA, and therefore radiation. This is a little advanced for this class, but for an introduction, with cath and angio, we were talking about the detectors. So you know how we said a minute ago that cameras can't capture full time? So why is continuous radiation a bad thing? If I can't capture this right here, here's my detector. It's only capturing at a certain frame rate. If I'm producing radiation the whole time, yeah, any problems with that? The patient is getting radiation, which is not being seen or used by the detector. Does that make sense? So that's continuous MA. What we're doing now, though, with modern systems is pulsing the MA to match the detector. So we're only giving radiation at the exact same time the camera, or the detector in this case, is pulsing. And this slide here, that's what this is talking about. Again, I'm kind of, this is a little in the weeds here, but on cath lab systems and CTs, they will apply a 3 kV bias voltage to these pins right here, negative 3 kV. So now these pins are at negative 43 kV. What's that going to do? When I turn that 3 kV on, it's going to stop that electron flow, because electrons want to flow from negative to positive, but now this area is more negative. So I can actually stop the tube current by turning this 3 kV on and off. So that's what this right here is showing. It's pulsing. Oh, maybe. Here. 3 kV, radiation off, radiation on. So this is called pulsed fluoro integrated X-ray tubes, and how we're going to control any modern system. All cath labs, all CT do it like this now, and they're actually going to pulse that bias voltage to start and stop the MA. So the KV is firing the whole time. There's a lot more we could cover here, but most importantly, I'm going to go to the very last slide, which is this one here. Everybody wants to talk about service access, and like right to repair is a big hot ticket item these days, right? Has anybody here ever heard of or filled out a 2579 form before? We know what that is. So what were you doing that required you to fill that out? Mind me asking? You replaced an X-ray tube. Great. What else? Inverter, multiplier, collimator. So the FDA has a form. It's called Report of Assembly. It's a 2579 form. Anytime that anyone, third party, OEM, anyone changes a certified component, you're required to submit a 2579 form to the FDA. Okay. So each manufacturer has a list of certified components, but in summary, if it makes X-rays or is in the beam, it's a certified component. X-ray inverters, tubes, collimators, detectors, some tables, the hand controls would not be, but if it makes X-rays or in the beam, certified component. Why do you think the FDA wants a form filled out anytime a certified component is replaced? Any guesses? They want to make sure you did what? Yeah, they're patient safety. They want to make sure you put this X-ray tube in and calibrated it properly. So the dose is what the screen says it is. They want to make sure that the collimator is working properly, that the inverter is working properly. It's all about patient safety. So you guys don't work for the OEM, but you still had to fill out the 2579 form. The OEM does as well. You probably never read the fine print. You just signed it, right? You sign your name, date, and you submit it. But this is the fine print. AIAT stands for Assemble, Install, Adjust, and Test. And this is the last paragraph of the 2579 form. No, actually, I don't have it here. The 2579 form, you say, I, Todd Boyland, certify that I have assembled, installed, adjusted, and tested this certified component in accordance with documentation provided by the manufacturer. I certify that I have assembled, installed, adjusted, and tested this certified component using instructions provided by the manufacturer. Why is that significant? The FDA says that we all have to do this using the instructions provided by the manufacturer. If a manufacturer tells you that you can't do something, I can promise you it's wrong. I've been at RSTI for 24 years. We've been in business for 38 years. We couldn't teach third-party imaging service. Think about it, right? If that was the case, if the OEMs could lock us out of everything, we wouldn't have jobs, right? So I'm just educate ourselves. If an OEM tells you can't do that, my card's right here. Please call me, email me. They're very good at scare tactics. You need this service key. You can't do this. You can't do that. I teach all these classes right now. I don't work for the OEM. That should tell you something, right? And while the 2579 form is kind of a pain in the ass, it actually helps us because it forces the manufacturers to provide these instructions to us. And they're called AIAT. So we could talk about AIT alone for a whole hour, but come see me at the booth if you have any questions. If an OEM tells you you can't service it because you haven't been to their training class or haven't got this key, I can tell you it's BS. There's hoops to jump through, don't get me wrong. They make it hard. That's what we do at RSTI. You need log in here, get his password, and we hold your hand. Here's how to do it for Siemens. Here's how to do it for GE. Here's how to do it for Philips. And you have to understand those hoops to be able to service these things. So appreciate you guys' time. Enjoy the show, and maybe stop by the booth. We'll see you guys in the exhibit hall. Thanks. My card's up here too. If anyone wants my email, any questions, come see me at the booth or grab a copy of my card.